All right, good morning. Good morning. Okay, so yesterday we talked about these Taylor polynomials and how we can use them to approximate certain values. Okay, so this warm-up is just practicing doing that again. So a couple different pieces of information. So the third degree Taylor polynomial centered around 2 for approximating this function. Okay, and then once we have that, if we can use it to then approximate what is f of 2.4. All right, and note that the thing we're trying to approximate is pretty close to what we're centered around. All right, we're centered around 2, so that means 2.4 is probably, whenever we do that, this Taylor polynomial will probably give us a pretty good approximation. If we centered it around 2 and then we wanted to know, what is f of 13, well, that's probably not as good of a value that we're going to get. Probably won't be as close as it should be, but it's centered around 2. We were approximating 2.4. It'll probably be pretty decent. I cannot speak today. Oh my gosh. But let's try it out. So the Taylor polynomial. So we call that P3. So that is, first of all, remember that first value is just f of 2, right? Since we're centering it around 2. All right, then we go to f prime of 2 divided by 1 factorial times x minus c plus f double prime of 2 over 2 factorial times x minus c squared plus f triple prime of 2 over 3 factorial times x minus c, which c in this case is 2. So cubed. All right, so this essentially is the Taylor polynomial. Now we just need to go through and do some simplification and actually figure out what some of these values are. So let's do f of 2 first. So that would just be e to the negative 4th. All right, not a super nice value, but a value nonetheless. Okay, I need to know these derivatives. So f prime, derivative of e to the x is e to the x, but since it's negative 2x, then we're going to have a chain rule. So this should be f prime. F double prime, so another chain rule. So we go to positive 4 e to the negative 2x. And f triple prime, using the chain rule, I would get negative 8 e to the negative 2x. All right, so now I just need to evaluate each of these derivatives at 2, since that's what we're centered around. So f prime of 2, so that's negative 2 e to the negative 4. F double prime of 2, is positive 4 e to the negative 4 f triple prime of 2 negative 8 e to the, again, to the negative 4. All right, since the exponent part doesn't actually change, since our function is e, essentially, e to the u, then the only part that changes is that coefficient that I get from using the chain rule. All right, so let's actually plug this in now. So I'm just using that same pink equation from above, and now I'm just plugging in the values that I know. So that first term, e to the negative 4th, if we want to, we could also write that like this, 1 over e to the 4th, whatever, doesn't matter. Okay, my next coefficient, so f prime of 2, now that's a negative, so I'm going to put a minus 2 over e to the 4th times x minus 2. And it was divided by 1 factorial, so just divided by 1. Okay, to the next term. The next term has a positive 4 as the coefficient. That's why I'm putting a plus sign. So plus 4 over 2 factorial times e to the 4th x minus 2 squared. Next term has a negative coefficient, so I'm going to put minus sign. Minus 8 over 3 factorial times e to the 4th x minus 2 cubed. We can go ahead and simplify these a little bit. All right, 4 over 2 factorial and 8 over 3 factorial. I can simplify those a tad bit, so I'm going to go ahead and do that. These first two terms, though, I'm just going to leave as is. But 2 factorial is just 2, so 4 divided by 2 will be 2. X minus 2 squared. Minus 3 factorial is 6. Right, 3 times 2 times 1. So 8 over 6. Simplify into 4/3. Okay, so here is my first part. All right, this is the third degree Taylor polynomial. So this is a polynomial that will approximate e to the negative 2x, and it's centered around 2. So it's a good approximation for things that are around 2, right, depending on how many degrees, what degree we go to. But the next part said, well, actually approximate 2.4. So f of 2.4, that would be approximately the same thing if I took my Taylor polynomial and I plugged in 2.4. All right, so if we took this wonderful equation and plugged in 2.4 for x, then what is the actual approximation we get? I don't know, but we could just type that into our calculators. I guess I'll go ahead and do it. One over e to the 4th minus 2 times x minus 2. So 2.4 minus 2 would just be 0.4. Denominator e to the 4th. Plus 2.4 minus 2 squared over e to the 4th minus 4 2.4 minus 2 cubed divided by 3 e to the 4th This is riveting content, I know. Very, very small number. Don't worry, I get the struggle. So the answer I got is about 0.00796. For the approximation. So now let's see if we actually plug it in. E to the 2.4 times -2. All right, so this is the actual value. If I just take my original function f and plug in 2.4, this is what I get. And this is what we get from our Taylor approximation. Okay, so they're pretty close. You know, they're off by, what, 5/10,000ths, something like that. Right, not even. Right, so pretty close to the actual value, which makes sense because we used a value that was close to where it was centered around with a third degree Taylor polynomial. Okay. Any questions on that? Laptop finally restarted. Amazing. Incredible. Some said it could never be done. I told them that it could be, though, so don't worry. Oh, man. Not a question. Yeah, nice try. Just say, my laptop finally restarted with a question mark at the end. My laptop finally restarted? Why use Taylor approximations if it's possible to find the actual value? Well, depending on things that we would want to do in the future, it's easier. It can sometimes be easier to work with the Taylor approximation, depending on what further math we need to do. And so can we say, well, is our approximation good enough that we could just use that? Because sometimes we use these a lot with functions like e and sine and cosine and natural log, right? Things that are not polynomials. See, the good thing about a Taylor function or a Taylor polynomial is that it's a polynomial, right? It's just terms of powers of x, right? Polynomials, x plus x squared plus x cubed plus x fourth with various coefficients and stuff. But it's a polynomial. And polynomials are easy to work with. Okay, they're easy. Polynomials are really easy to take derivatives of because we can just do the power rule. Polynomials are relatively easier to figure out what like zeros are. So when we're just doing calculus with these things, take derivatives, take integrals, it's much easier to do that with a polynomial than with certain types of functions. So if our approximation, if we can make an approximation that's good enough, let's just do it with that. Right. Also, like E in general, like how does your calculator know what the value of E is? So it's not just that the calculator has these values stored in there. For certain things like sine or cosine or E in your calculator, what the programming is actually built into it is it has a certain degree Taylor polynomial. And that's what your calculator actually uses to calculate the value. Instead of, sine and cosine and E and natural log, they're very, they seem more concrete to us because we can just type it into a calculator and figure out the value. But how do you actually figure out the value, right? Well, an easy way to do that is you can turn everything into a Taylor polynomial, right? Because polynomials are much easier to work with. Why use? Yeah, I think that answers it. I hope. And there's probably a bunch of reasons that I also don't know, but those are the ones that I can recognize as being the most useful. Okay, makes much more sense. Cool. Let's do a lot of reading here. So we're going to try to figure out how to find the remainder or error when using a Taylor polynomial. Since it's not perfect, it's an approximation. Can we figure out about how far off are we? So that's basically what this says. An approximation technique loses its value if you don't have an idea of how accurate it is. Okay, so just because we're doing these approximations, can we figure out, all right, I know this is approximate, but do I have a good range for how close am I? All right, when I calculate a value of a Taylor polynomial, can I say, like, well, I know this is within 10 of what I want? Is it within 1 of what I want? Is it within 0.1 of what I want? Okay, we can figure out how close are we. Even if we don't know exactly, we can approximate the error. Okay, so just, again, a lot of writing, but this is kind of the main idea, in that the exact value of a function is just the approximate value plus whatever's left over, right, the remainder. And what we call that remainder is the error. Okay, so Taylor's theorem. This is also called the Lagrange form of the remainder. For those of you that go into further math or physics, especially physics fields, Lagrange is a name you will know very well. Okay, if a function f is differentiable through order n plus 1 in an interval I containing c, for each x in I, there exists z between x and c such that... Now, this is just basically the Taylor polynomial, but it has that remainder added on here. So how do we find the remainder? Well, it is this. Okay, it is the n plus 1th term. Well, I guess, I guess that's a good way to describe it. Okay, where we take that n plus 1 derivative divided by n plus 1 factorial times x minus c to the power of n plus 1. So we're just, if we have a 4th degree Taylor polynomial, then to figure out the remainder and the error, then we consider, okay, let's look at the 5th degree. All right, let's look at what that next term would be, and we're going to use that to figure out about how off are we going to be. All right, now this is all very confusing in what all this stuff, oh my gosh, on what all this stuff up here says. So I'm going to explain that in the actual examples that we do. But the big thing is that there's going to be some z that exists between x and c. Right? X is the thing we're trying to approximate, and c is where we're centered around. So there's going to be some value in between what we're approximating and where we're centering. Okay, so this next page ties the actual thing. So this is our actual how we will determine the error bound. Okay, so this is the big important part. Right, so now we're using absolute value because we're saying once we find the error, is the error telling us that we overshot our approximation or we undershot our approximation? So we'll just create a boundary. We're saying, okay, here's what we got. Now we're off by this much. So that could be this much adding or it could be this much subtracting. All right, so that's why we're using absolute value. Okay. And we're going to look at this. This kind of looks like, I mean, basically looks like the Taylor polynomial formula. The only difference now is we're considering what is the maximum value of that next derivative, okay, evaluated at z. All right, so let's look at an actual example. Determine the accuracy of a 3rd degree Maclaurin polynomial to approximate sine of 0.1. Now, first off, let's remember what a Maclaurin polynomial is, right? This groundbreaking polynomial, which is just a Taylor polynomial, which is centered at 0, okay? So, crazy stuff. The problem is already telling us what the Taylor polynomial is. What a guy. How did he do it? You know, he was just sitting around, he's staring at those Taylor polynomials. He was like, come on, Maclaurin, think. What am I going to do here? What am I going to do? 0. Amazing. Okay, so it already tells us what I circled here in blue. This is the Taylor polynomial. This is the 3rd degree, or I guess Maclaurin polynomial specifically. So now we're just trying to do the new part of approximate. When we approximate sine of 0.1, let's figure out what would the accuracy be. Okay. So let me look back here, all right, at my, formula that I need. Actually, let me go ahead and just copy this down. Over here so we can look at it better. Paste. Boom. Okay. We'll keep it over here for safekeeping. Okay, so in this problem, I know what x is already. X is the thing that we're trying to approximate. So we already know the thing we're trying to approximate, or the value we're trying to approximate at, is 0.1. Right? I already know what C is, right? Because we're centering around 0. So N, in all of these, what is N? Well, N is whatever the degree is of this Maclaurin polynomial. So it's third degree. So now we're thinking of, oops, I guess this n. Let me use a different color here to keep this consistent. All right, so we're using n plus 1 because, again, like I said, we have to consider the next term. So we're going to be considering that fourth derivative, or 4 factorial, or exponent of 4. Okay, well, as I can see here, I need f, the fourth derivative of f. So let's first do that. So f of x in this case is sine that's the function that we're trying to approximate. So I'll just go through these derivatives. F prime is cosine. F double prime, negative sine of x. F triple prime, negative cosine of x. And the fourth derivative, again, we can write it like this, would just get me back to sine. Okay, great. I'm right back where I started. And more specifically, so from my formula, I want that value, well, so hold on. I want the maximum of this fourth derivative, right, if I evaluate it at z. Okay, now again, what is z exactly? Well, z is just some number that is between where, oops, I flipped those. Sorry, let me switch that. All right, is between where I'm centered at and between the actual x value that I want to evaluate. All right, well, we already know that c is 0, centered at 0. And we already know that x is 0.1. So z is something in between those two. Okay, so then if I want to consider the actual function, right, that fourth derivative of z, so sine of z. So let me just consider what would happen if I took sine of these things. Right, sine of 0 is 0. Right, less than sine of 0.1. And sine of 0.1, okay, as I'm alternating through here, sine in general, I know that the maximum value of sine is 1. Okay, so just to kind of make this easier on myself, I know then that sine of z, whatever it is, has to be some positive value that's between 0 and 1. So 1 is my maximum here. Okay, so that's that's what goes in this part of my remainder or error formula. Okay, we started off again just by knowing z is some number that's between the center, where it's centered around, and between the actual value that we're trying to estimate. So that would mean it's between 0 and 0.1. So if I think of what's happening at sine of those values, well, sine of 0 is 0. Okay, great. Sine of z less than sine of 0.1. And if I think of sine, the maximum value that sine can be is 1. Okay. So let's write so the error, well, I guess the error of the Maclaurin polynomial of the third degree, right, of 0.1, because that's what we're approximating. Okay, that absolute value is, so the numerator, absolute value of x minus c, so that's 0.1 minus 0. Okay, great. 0.1 minus 0 is 0.1. To the power of n plus 1, so to the power at fourth power, divided by n plus 1 factorial, so divided by 4 factorial. And then times that maximum, but like we just determined, the maximum value is 1. All right, so let's actually do this calculation really quick. So that gives me about 1/240,000th, or, you know, as a neat decimal, that would be like very small, 0, 0, I think 5. 1, 2, 3, 4, 5. Why wouldn't you just use the exact value of sine of 0.1? Wait, is that what you're asking? Why sine of 0.1? I'm assuming those messages are supposed to be together. You mean in the, for which part? What is n? N is the degree of the Taylor polynomial. So since it was a third degree Taylor or Maclaurin polynomial, Taylor polynomial, Maclaurin polynomial, whatever, a third degree Taylor polynomial, that's what we're using as n is 3. So that's why we're doing all of this to the fourth, right? So whatever degree our polynomial is, to figure out the error, we then consider that next term. So that's why we're doing 4 here and 4 here and the fourth derivative when finding the max. Oh, you mean like right here? This is what you're saying? Yes, because, well, so again, think about what our problem is doing, is talking about. This whole thing is saying Our whole thing is that we're trying to approximate sine of 0.1. So this is all operating under the assumption that we do not know what sine of 0.1 is, and for whatever reason, we can't figure out what sine of 0.1 is. Again, we have calculators that we can just we have a calculator that we could just automatically type in 0.1, right? The point of this is not that it's impossible to figure out what sine of 0.1 is, right? The point of this is how can we use the Taylor polynomials to approximate some values that we couldn't do. Does that make sense? Like, it wouldn't always be the case anyways that this just turns out to be some number that we could just immediately calculate, right? Since this is based on doing an approximation for that value anyways, so we're assuming we don't know that value. Right? This could all be done. I mean, save for this very last portion. Well, actually, even besides the decimal part here, getting to this answer could all be done without a calculator. All right, we could do every single step of this purely by hand. Okay, so this is an easier function. And again, we do have the ability to know what sine of 0.1 is, but we're just practicing using the Taylor polynomials to approximate things and how we would think about those error bounds. And it's sufficient enough just to know that sine will always be, the maximum value of sine is 1. So you could use it to approximate numbers that don't technically already exist. That's not... That's not quite the case, at least not the way that it's worded. But well, hold on. Before I go to that, does that make sense? My other answer of why we wouldn't just use sine of 0.1. Well, not that don't exist, that you don't have a decimal for. Right. Yes. Things that we can use this to solve for things that we truly can't just immediately calculate. Right? We can immediately calculate sine of 0.1, but if we had a more complicated function, or depending on the setup, there's also like certain differential equations and things like that that we can approximate a solution to, but without even knowing what our actual valid solution is. So will there be a time where we just don't know what the max is, given that we can't just plug it into our calculator? The exact value max, yes. But we should always be able to, if we can't get a value, we should always be able to use some sort of knowledge and intuition to determine a maximum value. So like, assuming we don't know what sine of 0.1 is, don't know what it is off the top of my head or whatever, I at least know that sine in general will never be greater than 1. So I can use that knowledge. Okay, and for our next one, I'll show you, it's kind of a similar thought process. Other questions? These are good questions. I like them. I hope I'm sort of giving an answer. All right. Okay, let's look at another one. Okay. Find the accuracy of the fourth degree polynomial of 0.3 to approximate y equals e to the x. Yeah, you guys can't see that. Let me move that down. Okay, so since this is talking about a fourth degree Taylor polynomial, and we're using it to approximate y equals e to the x. All right, this is one that we did last time. And so we see this is the actual Taylor polynomial. So we already did that part. And I guess to be more specific, this is a Maclaurin polynomial because it's centered around 0. So, again, let me bring this bad boy over so we can look at it and make sure we don't forget. Mostly for my own sake as well. Just so it's easier to look at because there's a lot of little pieces here. All right, this is our error bound. So n is 4 because it was a fourth degree Maclaurin polynomial. So we now want to consider n equals 5. Right? Consider the next term. Right, n plus 1. Okay, well, the first thing that I need, right, if I'm going to do the max of this, I need to know the fifth derivative. Well, that's really easy because our function is just y equals e to the x, and there's no chain rule or anything needed when I do these derivatives, so the fifth derivative is just e to the x. I'm so smart. Oh my gosh, I did it. Why is this? Okay. So let's look at that. So again, we have, just like on the last time, where we started here by looking at, okay, this z that we're talking about is between c and x. Okay, so I'll start there again. C in this case is 0 because it's Maclaurin, so it's centered around 0. Less than z. Less than x, which x in this case is 0.3 because that's the actual thing we're trying to approximate our function at. All right, but let's consider now our fifth derivative, because remember, this is all about taking z and plugging it into the fifth derivative, whatever it is. So let's do that. Well, e to the 0 is just 1. So e to the z less than, now again, e to the 0.3, we do have the ability to type into a calculator and get the actual answer. Okay, but the whole goal of this is saying we're trying to approximate because for whatever reason we couldn't actually do that. Okay, so we want to do this maximum part without using the function that we're trying to approximate. Does that make sense? Like our last one was sine, right? We were approximating the sine function. So if I'm trying to approximate the sine function, I don't then want to have the sine function in part of the calculation for my approximation, right? That's like it's just circular. Like, how do I approximate sine? Oh, just use this value of sine to approximate sine. Well, that doesn't make sense, okay? Because we're assuming we don't know what sine is. We're trying to approximate it. So if I have sine built into my approximation, it's like, well, I don't know what that is. I would need to approximate that sine, right? It would just be like recursive. It would be redundant. So same thing here. My function that we're trying to approximate is e, right? E to the x. So in my approximation for e, I don't want to use e, right? That's like, you ever hear people like define a word and they use the word in the definition of itself? It's like, well, that doesn't make any sense. It's like, what's the definition of angry? Oh, it's like when you feel really angry. Well, what? Well, yeah, I mean, so yeah, same thing. Like, we know what the word angry means, but if you're trying to define the word angry, you can't use the word in its own definition. I think that's actually probably the best way to explain it, at least in simplified terms. Okay, so we'll instead use our intuition to figure out what's an actual concrete value that we could do. Okay, so let's do some thinking. E to the 0.3 would be less than e. Okay, are we all okay with that? Right, e, which would just be e to the first power. E to the power of 0.3 would definitely be less than e. Okay, good to know. But again, not specifically helpful yet because I still don't want to use e. So now let me think of what is e less than. Well, I know that e is like less than 3. Okay, by the nature of e, I know that it's less than 3 because I know e is, 2 point whatever. So this is the value that we're going to use as our maximum. All right, 3. It's a concrete value, actual just straight up number that I can use in this maximum. Okay, so what is it? Fifth. Wait a minute. of x, which we know x, we're trying to approximate 0.3, so of 0.3 is less than or equal to, and then we just go through that formula that I have up there. So absolute value of x minus 3, so 0.3 minus 0, 0.3 to the power of n plus 1, so to the fifth power, divided by n plus 1 factorial, so divided by 5 factorial, times the maximum of that fifth derivative at z, which we've intuitively determined is 3. So times 3. And then the fifth times 3 divided by 120. So a very, very, very small number, which in scientific notation would look like this, or if we wanted to actually write that as a decimal, oops. So let's see, 6075. Boom. Always got to count to make sure. So this is my error bound. This is how close I know that my Taylor polynomial. All right, if I'm using this fourth degree Taylor polynomial to approximate e to the power of 0.3, that's pretty damn good. My answer is only going to be off by 6075 100,000ths. It's really close. All right, so that's why it doesn't take much. Only a fourth degree Taylor polynomial gets us there. All right, it doesn't take a whole lot to get some really good approximations. This is super close. How are we doing here? Are we totally lost? Should I quit my job? Please say yes, 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 please say yes. I'm great. Thinking I'm going to have to rewatch this, though. Okay. That's fair. Thanks, Mom. Okay, so it's a lot of just familiarizing yourself with the formulas. Okay, just like with the Taylor polynomial. Yeah, there's a lot of small pieces and details to memorize. And that's kind of the worst part of it. All right, but whatever our Taylor polynomial is, make sure that the remainder, to calculate that error, we got to go to the next term. So if this was a 4th degree Taylor polynomial, that's why we had to do the 5th derivative and to the 5th power and divided by 5 factorial. So that tells us how far, at least the range of how far above or below the actual answer are we. We're within that range somewhere. And so I do think that is the best explanation for the maximum part, though, of what, I forget who asked. I think Forrester asked at first. Like, at this point, you know, well, e to the 0.3, why would I not just use that? You know, that's just a number. Why would I not just use that as my maximum if we know it's already less than that? Well, again, so like I said, think about it. If you're trying to define a word, you don't use that same word in the definition, right? Just because you know what the word means already. So I guess it technically makes sense, right? But so we're trying to approximate E already, so we don't want to use E to tell us how far off from E are we. Okay. Have I fried us completely? Should I go on to the last problem, or should I just save that for tomorrow? Let's keep going. Keep chugging along. And then we'll all go back and watch this on YouTube too. And then we'll also go back and watch it on Mixer. All right, and then we'll also go back and watch it on Facebook Live. And then also, if you go to Abundus Does Math Instagram, this is all part of a 45-part story that you can also watch it on there. So just whatever's easiest. Great. Okay, so let's look at this then. All right, so we have a table of various values here. Let's shift these down so that we can see them better. Oh no, can I not move it? I guess not. Well, I tried. I mean, the only thing you really can't see is that says, that top right box says f triple prime, right? The third derivative. Okay, so we're starting off just given a table of values for x, f, f prime, f double prime, f triple prime. Part A tells us to find the second degree polynomial to approximate f. Part B, use that second degree polynomial to approximate f of 1.8. And part C, find the maximum error. Okay. So just as I glance through this, in part B, The thing that I'm going to end up trying to approximate is 1.8. So for part A, when it asks me just to find the polynomial, right, find that second degree Taylor polynomial, my question to myself before I start making this is, where should I center this? Or where should this be centered? Because at least as I initially look at this, I have three options. I could center this at 1, I could center this at 2, I could center this at 3. Because remember, the very first term of the polynomial is always just f of wherever I'm centered around. So should I make that 1? Should I make that 2? Should I make that 3? What do you guys think? Where should I center it? Which one would be the best choice? Two. Absolutely. Okay. Yes, Reese. Yes, RJ. It would be the best to center it at 2 because we're trying to approximate 1.8. Right? So always to get our best approximation, we want it to be centered around some value that's the closest to the thing we're trying to approximate. Let's get some hype. Come on, hype them up, guys. All I had to do was ask RJ a question that had 1.8 in it, a decimal, and he just instantly knew. Okay, so that first value will be f of 2. Now think of, I'm just going through the Taylor polynomial formula right now. So next is f prime of 2 divided by 1 factorial times x minus 2, because that's where it's centered, plus f double prime of 2 divided by 2 factorial times x minus 2 squared. All right, and I can just stop there. Oops, not that one. Because all I wanted was a second degree Taylor polynomial. So once I get to that term that has second derivative divided by 2 factorial x minus c squared, that's where I stop for it, because it specifically tells me do a second degree Taylor polynomial. Okay? So now I just need to simplify this by actually getting the values. But so the only things I don't know yet are what are f prime of 2 and what are f double prime of 2. But I know those. F prime of 2, f double prime of 2. Question, do you have to put the 1 factorial? Was it just part of the process and you wanted to show us that? Yeah, I'm just showing you, just practicing drilling that formula into your head. Right, and that way it's easier to see the pattern. But yeah, I mean, you don't have to write divided by 1 factorial. But it just helps, I think. I always write it, even if I weren't teaching, I would typically write it. So f of 2 is 1 plus f prime of 2 is also 1. So 1 over 1 factorial. So plus x minus 2 plus f double prime of 2. So that's 1.5 divided by 2 factorial, which is just 2. x minus 2 squared. I hate this 1.5. Let's change that. Quick, RJ, what's 1.5 as a fraction? Quick. Every time, man. I'm gonna quit my job. Well, what happened? My mom said no, I know. But when's the last time I really listened to her? Okay, 1.5 is 3 halves. So 3 halves divided by 2, 3/4. Okay, so here's the second degree Taylor polynomial. Okay, so now, next, let's actually use this to approximate f of 1.8. So we just take our polynomial and plug in 1.8. Okay, 1.8 minus 2. So that's negative 0.2 plus 3/4. 1.8 minus 2, negative 0.2 squared. Do some calculators. Okay, and we would get 0.83 or 83/100ths. So f of 1.8 is approximately 0.83. 830 over 1,000. This is why I wake up in the morning. To come read this chat. Okay, find the maximum error. So our error formula, reminder, is this. Assuming I can remember it, let's see, n plus 1 over n plus 1 factorial f, max. Right, n plus 1 of z. You probably can't see it. right, so since we used a second degree Taylor polynomial, that means we're now considering that next term. So now I'm considering to the power of 3, or divided by 3 factorial, the derivative, the third derivative. All right, so usually we had to go through and do the derivative of each thing, but we don't even have an actual function here. Right, but so z is something that is between, remember, c and x. Okay. C in this case is 2, because we know that's what we centered it around. And x in this case, 1.8. Okay. Oh, actually, I should flip those around then. All right, z somewhere in between there. But let's look at, we actually know specifically the third derivative of 2, right, is, let's go up to our table, is 2. Right, so I really don't even need to do speculation about when I plug in and make, linked connections. I just know it's already that maximum, no, sorry. The actual value of the third derivative at 2 is 2. Okay, so I can just use this for my maximum. Just let's go ahead and erase this part. Okay, so R2 of 1.8 is less than or equal to, so absolute value of x minus c to the power of n plus 1. So x minus c is negative 0.2, but we're taking absolute value. So 0.2 to the third divided by 3 factorial. And so we know that maximum value is 2. Right, because I know that z, whatever it is less than 2. And so if I think about comparing the third derivative at z compared to the third derivative at 2, well, look at our table and look at what we know. All of the derivatives are positive and increasing. Right, so we go from, 1 there, we're increasing to 2. So since z is something that's less than 2, I know then the third derivative of z must also be less than the third derivative of 2. All right, so that's why I'm using this 2 as my maximum value. All right, it's not the fact that it's centered around 2. That's just, I know it's kind of confusing, but it's coincidence. The 2 that I'm talking about is what is the third derivative of 2, or the third derivative evaluated at 2, I guess, to be more specific. That's where this 2 comes from. And if I just calculate that, let's see, something quite small again. 0.2 cubed divided by 6. Oh, I guess I could have done that. 1/750th. So pretty good. As a decimal, that's how far off we are. So here's the approximations we got. And then here is the maximum value of how wrong we are. So we can't be that wrong. It's pretty dang close. All right, again, it could be 0.0013 above the answer we got. It could be 0.0013 below the answer we got. Could got between what we did get. All right, and that's just the maximum error. That doesn't tell us exactly, this is exactly how wrong we are. No, that's not what it says. It says, this is the possibility of the most wrong that you are. So it's also possible the real error is actually less than that. Maybe we nailed it closer than we thought, closer than this. But this is just the maximum value of how wrong we could be with our approximation. Okay. That was rough. We're going to continue talking about some examples of this tomorrow. We're going to do another day where I don't know that we'll learn anything new tomorrow or Friday, but we'll at least spend time just doing more of these examples together and seeing some slightly different worded questions, but still just basically doing Taylor polynomials, doing Maclaurin, and doing the error remainder. Okay, so we're still going to keep working on that. We're not done just yet. But here's some homework problems. So highly recommend going through working on these. The ones that are paired up, so the reason that they're paired like this is because they use the same original equation. The first part just says find the Taylor polynomial. So that's what 17, 28, and 30 say. But then 39, 41, and 42 say, or I guess not find, use the Taylor polynomial to approximate some value. All right, but and it says this in the book as well, but when you go to question 39, in parentheses next to it, it says like exercise 17. So you use the Taylor polynomial from exercise 17 and actually approximate the value that it asks you to approximate. All right, we just did all those, together. It would be basically like the first of those pairings is like part A, where it says find the polynomial. And then when you go to that next question later on, it's like part B, where it says, okay, use it to approximate something. So that's why I wrote it like that. But again, it says it in the book. 45 and 48 are practicing doing the error. Check those out. But ran a little late today. Sorry about that. But any final questions here or comments? Nope. All right. I had fun. I hope you did too. I will see you tomorrow then. We will keep practicing various Taylor stuff. You shook your head no. Thanks. Appreciate that. It's been a long day. It's 10:37 a.m. But, oh, did Miss Leah make you get up at 4 a.m. to start your Zoom meetings and homework? All right. Since we're running so late, I need to go head to a mentor check-in. So Hayden, you go to yours too with Miss Lee. And I will see you guys tomorrow.